Okay, I will share my screen.
Yeah, so I will give you an introduction, then you can start your talk.
Okay.
So let me do it. So yeah, so our first invited speaker will be Yisen Wang. So Yisen Wang is an assistant professor in the Department of Machine Intelligence, ECS at Peking University. He got his PhD degree from the Department of Computer Science and Technology at Tsinghua University. His research interest broadly includes the theory and applications of machine learning and deep learning, such as adversarial learning, graph learning, and weakly and self-supervised learning. So the talk title is Rethinking the Training Objectives for Robustness and Privacy. So let's welcome him to give the talk. Yeah, please get started.
Okay, could you see my screen?
Yeah, I can see your screen.
Okay. Thanks for the introduction. I'm very glad to be here to present our recent work about the training objectives for the robustness and privacy. I'm Yisen Wang. Yeah. Currently, I'm an assistant professor at Peking University. So as introduced by the Professor Dang Zong, yes, machine learning currently is almost everywhere in our everyday life. Such as we use it every day, such as the speech recognition, image classification, or the objective detection. Okay, maybe in the future, the autonomous driving will go into our life. But however, for very simple tasks, just like classification tasks, this is given a pre-trained neural network, just like a convolutional neural network. So we given his a dog here, no surprise, it will classify the dog correctly. Okay, if we given his another example, so the difference is highlighted by the red point. But note here, the red point is not the actually added, just showing, highlight the difference between the two figures. If we given this example to their neural network, it will classify wrongly. This is not a dog, and give a very high confidence. So maybe you can think the classification is very simple. So it is maybe far from our everyday life. So maybe I will show you this example. This is the autonomous driving system. Maybe this is it is a safety critical application. So you can see in the left figure, this is the natural scenario, and at the corner, the autonomous driving system will make the car turn red. But in the red figure, you can see that in the roads there are two black lines in the road. Maybe these two black lines can be the shade of something, or the emergency braking. But under this situation, the autonomous driving system will make a wrong decision. It will make the car to turn left, and then it will be an accident. So this will be very dangerous. So for another system, this is the CCTV system. You can see here is a student, and he wear a t-shirt, and there is a small patch, image patch in the front. And you can see if the patch is covered, so the person can be detected by their monitor. But if the patch is showing up, it's not covered, and the person will be not be detected by the monitor. That means that he can remove himself from the monitoring system. So this is also very dangerous for the security camera. So maybe we want to know how did this happen. So this is I will make a very quickly brief review of the adversary example. Note that here I only mentioned some of works in the digital scenario. Maybe there are another lots of works in the physical attack. So we know the model training is just like the traditional ERM training. So that is, we want to find a lot of a set of parameters theta and to minimize the loss function on the training set. So the adversarial attack is just the one to maximize the loss to find the X prime here, and which is very close to the original example. But his target is to make the model to do misclassification. So there are two very well-known methods to do the adversarial attack. So the first one is the fast gradient sign method. It's called the FGSM, and the other one is the projected gradient descent. It's also called the PGD. It is the iterative version of the FGSM method. So this is a very quick review of the adversarial example. So I will put more attention on the how to obtain the adversarial robust models. So maybe currently is the most promising and effective one is the adversarial training. So the adversarial training can be formulated as the following min-max optimization problem. We can say it has the inner maximization and the outer minimization. So the inner maximization is to generate the adversarial examples by maximizing the loss function. So you can see that this is a constraint optimization problem. And the outer minimization, it is a typical process to train a model, but this is on the adversarial example, not all the natural or benign examples. So from this min-max optimization procedure, we can see that how well the maximization is solved, it will have a great effect on the minimization process. So a natural question is here, we want to know how well the inner maximization is solved. So here we, in our work, we propose the first order stationary condition we call the FOSC here. We want to, it is the maximization of an inner product of the difference and the gradient. So it has a very good properties. First one is the FOSC value. If the FOSC value is very small, it shows that the inner maximization is well solved. If the FOSC value is very large, it shows that the inner maximization may be not well solved. The second property is it has the closed form solution, so it will be very easily to use the monitor the training process of adversarial training. So another theoretical property is that given the FOSC environment here, we can prove that if the inner maximization is solved to precision, the whole model, the adversarial training can converge to the first order stationary point. And if the FOSC value is small enough, so here is the data is small enough. We can see that the adversarial training can theoretically find a robust model. So beyond this theoretical result, I want to intuitively show that why do we need FOSC value here? Because we already has the loss function to monitor the inner maximization solving process. But here we have tried different adversarial training with different PGD parameters. Maybe only two parameters here, the PGD step size and the PGD step number. So here there are two subfigures here. The left two figures is the robustness with different PGD configuration. And the right two figures is the loss distribution. We can see that different PGD configurations will lead to different robustness. But for the loss function, we can say his loss distribution is almost the same. So we can conclude that loss is not a good indicator for the training process. So here we show the FOSC here. The two figures in the middle is the FOSC distribution. And if we compare the left four figures, we can see that for the step size, the parameter, we can see the the highest robustness is obtained by the PGD with the step size of epsilon divided by 2 and epsilon divided by 4, and its corresponding Fosk distribution, we can see that their Fosk distribution is more close to 0. That means that most of the values of Fosk is close to 0. That means that the inner maximization is solved relatively well. So it leads to the good robustness. Well, for the another configuration of the step number, we can see for the different step numbers, their robustness is almost the same. But correspondingly, its Fosk distribution is also almost the same. So here we can see that the Fosk is a good and a reliable indicator of the final robustness. So with the Fosk at hand, we can do the another thing is that we can using Fosk to understand the training process of adversarial training. So here we choose the 3 stage of the adversarial training. We using the epoch 10, epoch 60 and epoch 100 to choosing the 3 stages of adversarial training. We call it the early, middle, and the later stage. And we can see that at the early stage, the Fosk values may be close to 0, and as the training goes up, and the Fosk value becomes large. So this is not what we expected. So we conjecture that maybe this is due to the standard adversarial training. It's overfit to the strong PGD adversarial example at the early stage. So another very straightforward idea is if we replace the early stage PGD adversarial example using some weak attacks such as the FGSM here, and we can find that if we using FGSM first and then PGD, it will improve the robustness maybe 2 or 3%. And this improvement can also be verified by the Fosk distribution, as shown in the figure C here. We can see that at the final stage, the Fosk distribution maybe the 40% the values is close to 0, and comparing to the result in the figure A here, we can see in the final stage it's Fosk values close to 0 only consist of 30%. So most of values is close to 0, so it improves the robustness of adversarial training. So this is also explains why warm-up techniques works here. So maybe we can using a lot of warm-up techniques such as curriculum learning or something else. That means Fosk, from the Fosk view, curriculum learning work because it make Fosk values more and more Fosk values close to 0 in the training process. So it will improve the final robustness. So this part is we showing that the warm-up is a method to solve the maximization problem in the min-max optimization process better. So is there other option to do this? So this is our another work trying to rethinking this problem from the robust generalization gap perspective. So this is the min-max optimization problem I have mentioned before, and we can rewrite it as a mean problem. But here is the mean rho W here, but here the rho W is the maximization precise. So we first comparing with the standard training. We know standard training just here the rho W do not have the maximization precise, so it only has only the ERM training, and this is the training precise, and we can say here the generalization gap. Here we call it the standard gap. It is very small. The gap means the training accuracy, the difference between training accuracy and the test accuracy. But for the adversarial training, we can see that this is the robust gap. And we can see the difference between the training robustness and the test robustness, the gap is very large. So can we do something to minimize the gap? So we get the inspiration from the standard training. We know at the standard training, it has the conclusion that the flatter weight loss landscape and will leads to the small standard generalization gap. So here are the two figures. We can see the left one is the loss landscape of a model without skip connection. We can see that it has a lot of sharp point here, and you can imagine his generalization will be not good. But the right one is the loss landscape of a model with skip connection. We can see that it makes the loss landscape flat. And this will lead to the smaller generalization gap and will be the very good generalization performance. So here we want to know, is this conclusion still existing in adversarial training? So we want to explore this problem. We're using the visualization method from the NeuroSport paper. And we know the standard training the loss landscape is plotted by the given the training data, and we perturb the model in the direction of D within the attitude of alpha, and then we plot the loss distribution under the training data, and we got the loss and escape. So similarly, in the adversarial training, we can naively to replace the normal standard training example using the adversarial example. So we can know given a model and given a data set, we can easily pre-generate a lot of the adversarial example of the data set. But we know this is the pre-generated adversarial example. Unfortunately, under this situation, we cannot draw the conclusion. But with rethinking this problem, we think that the visualization method cannot be directly transferred to the adversarial training scenario, because we know that adversarial example is highly correlated with the model. You know, if we already perturb if we plot the loss landscape, we already perturb the model. So the model is changed. So if you use the pre-generated adversarial example, it's not suitable for this situation. So here we think the correct way is that we should generate the adversarial examples on the fly. That means that if we perturb the model, and then we need to solve the maximization problem again to generate adversarial examples. So here, and this we think the right loss landscape visualization method, we can say in the training process of the adversarial training, in the early stage, the gap is very small, so the loss landscape is very flat. And as the training goes on, and the gap becomes large and large, and the loss landscape also becomes sharper and sharper. So here we can see the weight loss landscape has a strong correlation with the robust generalization gap. And this phenomenon is also existing across different adversarial training methods. Here we compare the adversarial training, trade, smart, IST, and adversarial training with early stopping, and we still have this phenomenon. Theoretically, we can informally from its Peck-Basin bound, here we can say actually it has the term, currently the second term. It has the term in the bound. It is about the flatness of the weight loss landscape. So we can implicitly to add the weight loss landscape regularization in the training objective. So here we simply replace the expectation here by their maximization. So we propose the adversarial weight perturbation method. We will call it AWP here. So we will change the problem from the min max problem to the min max max problem. The first inner max is on the input, and the second inner max is for the weight. So here the two max together is to make the maximization in the left equation to make the maximization solves better. So here I want to provide some iterative understanding for their two kinds of perturbations. You know, for the input perturbation, currently the model is fixed. That means that the input perturbation is a local worst for each example, and the weight perturbation, you know, the weight is will affect multiple examples. So if we do the weight perturbation, we can affect multiple examples. So it is global worst case for multiple examples. So the two max together will find more worst case adversarial examples in the min-max training objectives. So within this objective, we can find that it is the universal robustness improvement under the different adversarial training variants, under different adversarial attacks, whatever the white box, the black box, and the auto attack. Another I want to mention is that the pre-training within the big data or big model is very popular in these days. But here, a good message here is that if we using some new algorithm, we can also beat the pre-training method. So here we can see the traits with AWP, and it will outperform the pre-training method. Also, pre-training also will help the new algorithm. So you can, if the pre-training plus the AWP, we can obtain more gains here. So previously we are all talking about the maximization process. So here I will talk about the mean process. So this is still the problem. Recalling that the adversarial example is officially or formally defined on the correctly classified example. So how about the misclassified example? It means that if the example is not correctly classified by a model, so how to define his adversarial example. So here we first analyze the two kinds of examples influence on the model's robustness. So we're using a pre-trained network to select the two subsets. One subset is the misclassified example, and another set is correctly classified examples. So from our experiment, we can find that the misclassified example has a significant impact on the final robustness. So to further, we want to know which process will influence the final robustness from the max or the mean process is more will affect the final robustness more. So here for the inner maximization for the outer minimization, we have tried different methods, different controllable experiments. And we found that different maximization techniques has negligible effect, but the different minimization techniques has significant effect here. So based on the adversarial risk, we separate the data into two subsets. One is the correctly classified, one is the misclassified. And then we put this one to the adversarial risk, and we will derive the following misclassification aware adversarial risk. So here we can see that he make an emphasis on the misclassification examples. So we have tried different surrogate laws for their misclassification adversarial risk. So we propose the method called the misclassification aware adversarial training, also called MART here. And it has three terms. One term is the first term is it's called the BCE here. So here is the marginal, it is the margin loss. And the second term is the KR divergence. That's just the same as the trade method, but difference is it has different weights on the KR divergence. The weight is based on the prediction probability. And we have trying conducting a lot of ablation studies here, just include the removing or the replacing and showing that the current version of MART is the optimal. So all the above is about the robustness. So the last part is about can adversarial be used for the privacy. We also talk about this problem from the objective functions perspective. So we know there exists a lot of privacy protection methods We know there are encryption method, federated learning, or differential privacy. But here I want to mention the method from the adversarial machine learning. So we know two kinds of methods, just like mentioned by the Professor Dang Song before. Adversarial examples can also be used for privacy because you know, just like the video here, you can wearing a very special t-shirt, and then you can remove yourself, just hidden yourself in the camera. And another one is the backdoor attack. That means that you can wear a trigger, and then when you're passing through a backdoor model, and you can trick the backdoor model to classification wrong and something else. But the final goal is you do not want the camera system to recognize you correctly. But you know, here the two kinds of adversarial machine learning methods here, you know, we must wear something. No matter the adversarial noise or the trigger, we must wear something in the test time. So we want to do something new here is that we want to make the machine learning model fail to recognize yourself, but you do not do anything in the test images. Just here is the unchanged test images. So we want to modify the training process. So we want to train a machine learning model with the modified examples, and to protect the stillness. So the modified image, it should be virtually the same as the original images. So here we propose the modified image as the unlearnable examples. So what does the unlearnable example mean here is that it is very similar to the adversarial examples. The difference that adversarial examples just want to make the model make wrong prediction. But here, the unlearnable examples is want to make the example unlearnable. Unlearnable means that the error here, we want to add some noise to the image, and then we will make the loss directly goes to zero. That means that when you're given an image and the image adds some noise, and then it will feed into the neural network, and it will got a loss of zeros, so it will learn nothing from the image. So this, so here we call the if we call the adversarial noise as the error maximizing noise. So here unlearnable example, it uses the error minimizing noise. So this is the corresponding notations. The difference that the unlearnable example is the training time attack, and its target is to minimizing the errors. So here is the visualization. This is the author list of our paper. So the first row is the original image, and the second row is the unlearnable image. We can see virtually they are almost the same, just like the adversarial examples. But the first row's image, when it fit into the neural network, its loss is somehow very large. But the second one, when fit into the neural network, its loss will almost zero. So we have to study on the face recognition system. You can just you can imagine a scenario like this. You have your photos, you have your self photos, and you want to post it on the Twitter or the Facebook, but you do not want to leakage your information. So you can using your data, and then you collect some others facial data sets, something like from the Setba data set or something, some others data set. Then you can building a small model in your local computer, and then you can generate some error minimizing noise, and then you can add this noise to your self photos, and you can create the unlearnable images. So currently your work is done. You do not care about what's the following process. You can secretly post your photos to the internet, and then maybe there are other companies to collect the data for their DNA training. They will train the face recognition system. No, you do not care about it. Then you're walking in the street, and a camera will capture your face, but under the unlearnable examples, the red figure shows the result. If the image is unlearnable, so its classification accuracy is very low, just around maybe the 10%. And when the photo is do not add any noise, do not do any privacy protection, its classification accuracy is very high. So here we want to say if you want to know more the facial recognition, you can just post the unlearnable image to the internet. So this maybe my introduction to our works is very quickly. Do not cover many details, so you can review our papers. This is the mentioned papers in this talk, and thanks for your listening. Yeah, this is all.
Yeah, thanks Isa for the great talk. So for the audience, please post your questions for him. And let me ask the first question. So in the first part of your talk, you kind of mentioned that to avoid the model to overfit to PGD attacks, you train the model on fast gradient descent adversary samples first, and then add the PGD attacks in the later stage. So have you tried if you simply kind of mixing both kinds of adversary samples during the full training time? Does it change the performance, or is it critical to have to focus on PGD attacks in the later part of the training?
Yeah, this is a very good question. Actually, I have tried, maybe we have mixed different kinds of adversary examples, just as the FGSM and the PGD examples mix up. And we find that maybe it very like the normal DN training like that. It will first learn the easy example. FGSM is very easy example, so it also will learn the FGSM first, and then he will focus on the PGD examples. Just like I think the idea is very similar to the curriculum learning, just learn easy first and then harder. Just the learning process is progressively hardening the process. Yeah. And this process is also improve the robustness, maybe 1 or 2% improvement. Yeah.
I see. So basically, you are thinking that kind of progressively increasing the difficulty of adversary examples is the best choice.
Yeah, correct. Yeah.
Then the next question is you also show if you can flatten the weight loss landscape, then it could further improve the robustness. So I wonder when you kind of change this objective function, is there any drawback? So for example, does it make the training harder or taking more time, or it doesn't affect or even improve the training process?
Yeah. It's also a very good question. There is no free lunch. So if we change the min-max problem to the min-max problem, the training time will be the overhead maybe from my memory, the overhead maybe the 8%, the overhead of the training time. But you do not to worry about this, because here the maximization on the weight perturbation, it will only do one more back propagations. So most of the time is still on the PD adversary example generation. Yeah, not because the weight perturbation we can you can think the weight perturbation is just like the one-step FGSM, but the inner adversary example is also the multi-steps PGD attack. So the most of the time occupation is still on the adversary example generation. Yeah.
Yeah. So in terms of the convergence time, so basically you are saying that it also converges within a similar number of epochs, so it doesn't need to take a longer time.
Yeah. It do not need to very longer epochs. Maybe 100 and 100 is enough. Yeah.
Yeah. Great. So the next question is kind of pretty it might be a pretty general questions about the defenses. So you have shown a lot of great work for the adversary defense. So could you so I think in most of existing works there has been showing that there is a kind of fundamental trade-off between the accuracy on the benign data and the adversarial accuracy. So like with all the defenses you have discussed, and especially many of them are backed with some theoretical analysis. So like do you have like some new thoughts on it? So for example, how to like mitigate this trade-off?
Yeah, actually, from our experiments, we definitely find the trade-off existing and cannot be simply mitigate. But I think maybe we need to involve more information, because just given the data set, if we do anything, I think if just giving the data set, if you do not have extra information, no matter what you do, the trade-off still exists. So maybe you can involve some more information that's just like the domain knowledge, or something like the knowledge transfer, or something else. Then you can maintain a very good standard accuracy. Then you can do something else to improve the robustness. So maybe we need the more extra knowledge to maintain maybe the accuracy of the robustness, and then we're doing some algorithm modification to improve another one. Yeah, this is my personal point. Yeah.
So for example, one idea maybe related is that, for example, you can have like more like a clear definition of your input distribution, and you optimize towards it. Then maybe it might be easier to like also enforce the robustness, while the accuracy on this distribution might be like a better control.
Yeah. I think so. Yeah.
Yes. So thanks a lot for your great talk.